Hey guys, today you will learn, you're here to learn about IB Chemistry HL stoichiometric relationships. The HL part, there, everything from the first chapter, the SL and the HL people need to know. The HL is just there, but the SL people also benefit from this video, hopefully. And I'll just start. Hopefully this video will help you understand the basics of this topic. I won't go super in depth, but I will definitely touch on every point. It won't be too shallow, it won't be too deep. This is like an overview, so you would know what points you're stuck at and what you need to work on. And this just basically goes through the whole chapter. Alright, so I would like to begin first of all by something really simple. I assume you know the basic stuffs, alright? The basic stuff. But I will just start, alright, with something pretty basic from the same chapter, which is balancing equations, since we don't need the introduction anymore. So if you look at this equation over here, Ca plus Cl2 equals a calcium chloride. This is balanced. Why? Because you have one calcium, right? That's one, and you have one chlorine, right? You have two chlorine, I'm sorry. Why is it two? Because you have the two over here. This is one side of the equation. This is the left side, and that's the right side. I mean, that's how I remember it. So we have whatever we have on the left is equal to whatever we have on the right. And it's exactly the same thing as we have in math, balancing equations. Everything's pretty much the same. Now on to my second example where, things get a little bit more challenging. If you know this, not that hard. Is this balanced? And the answer is no, this is not balanced. Why? Because you have the hydrogen over here, right? You have two hydrogens, right? And we can say two hydrogens because of the small subscript written right there. And oxygen, we also have two oxygen over here because of that. This is not balanced. Why? Because we have one oxygen here on the right side, but on the left side we have two oxygens. So in order to make that balance, what we do over here is that since we can reduce the numbers, we can increase them because of the ratios. So we added two over here. So now we have 4 hydrogens and 2 oxygens. So we multiply this side by 2. So what does that equal? Just the hydrogen, not the oxygen, because you have a plus over here. Just because of that, what happens is that we have 4 hydrogens now. Instead of 2 hydrogens, we have 4 hydrogens now. And oxygen still remains a 2. 4 hydrogens on the left side, 4 hydrogens on the right side. On the left side, 2 oxygens. On the right side, we have 2 oxygens. As you can see, we'll multiply this side over there. So that is the the gist of balancing equations. In solids, this is what you have. You have all the particles arranged close to each other, so that's a solid. For liquid, sorry about that. A liquid, even the particles are close to each other, but they are more spaced. And water is an example of liquid, right? And liquid does not have a definite shape. It can take the shape of the container that's in. But solid can't. It's just a solid piece. Just as the name says, solid, liquids, and gas. And gas are spread out. They have, they don't have any forces between them to hold each other. They have no fixed shape and no fixed volume. So a good example of this is water. Ice is solid, right? Liquid is the normal state of water, and gas is when water evaporates. That is right. So from these examples, over here I'd like to ask a small question to make sure if you guys are following along. Which of the following would have the highest average kinetic energy? The answer would be the highest kinetic energy would be number 4. Why? Because it's at the highest temperature. The higher the temperature is, the more kinetic energy. Now I'd like to talk about Avogadro's constant, which is 6 times 10 to the power of 23. This number is a definition of a mole. This number is a definition of a mole, and I'm pretty sure you've seen that already in chemistry class. just like a dozen is 12, a mole is 6 times 10 to the power 23. That's a really big number. You could have a mole of donuts. You could have a mole of anything, basically, because it's just a number. A mole of eggs, and that's a really big number. But you could have a mole, I mean, just like a dozen eggs, you have a mole of eggs, which don't really exist, but you get the idea. It's just a number. If you have 6 times 10 to the power 23 hydrogens, like that small plus, right? Hydrogen. If you have 6 times 10 to the power 23 hydrogens, that would equal 1 gram. And if you have 6 times 10 to the power 23 oxygens, can't spell, that would equal 16 grams, just as it says on the periodic table. Atomic mass on the bottom. So atomic mass of oxygen would be 16. It's pretty close to 16. And for hydrogen, if you don't believe me, would be 1. Because a mole of hydrogens is equal to 1 gram. A mole of carbon is equal to 12. Yeah. The empirical formula gives a whole number ratio for the elements in its compound. The molecular formula might be C2H4. You see the connection over here. The molecular formula, right, it gives you the actual number of atoms in a molecule. So this would be the molecular formula. That would be the molecular formula. But since if we are finding the empirical formula, and most questions will ask you to find an empirical formula, that would be the simplest ratio of the formula. So we know that there are 2 carbons for 4 hydrogens, right? And we know that we can reduce that number by dividing it by 2, and we can have 1 carbon for 2 hydrogens. And that would be the empirical formula. Formula. The question mark in there. Now I would like to bring your attention to a new unit. We have, we all know that we have the Celsius scale for measuring temperature and the Fahrenheit scale for measuring a temperature. Later, like, why do we use Kelvin instead of Celsius? But 0 Kelvin is equal to negative 273 Celsius. So we can see minus 273 degrees Celsius is a really cold temperature, like really, really cold temperature. In fact, it's absolute 0. And that's where Kelvin comes in. At 0 Kelvin, all the molecular activity stops at negative 273 degrees Celsius, meaning we cannot go further than that. That's the coldest that anything could ever get. All you need to know for this is that 0 Kelvin, it's not 0 degrees Kelvin, 0 Kelvin is equal to negative 273 degrees Celsius. Just keep that in mind. Alright, at this point, I would like to introduce the different formulas that come in this chapter in stoichiometry. So the number of moles, let me add that. The number of moles is equal to the mass over the molar mass. Right? Usually in a question, you might be given the number, you might be given, questions comes in all all shapes and sizes, right? Obviously, you could have number of moles, right? And you might have to find the mass, and they would not give you the molar mass because all the information for the molar mass is found on the periodic table. So for example, the molar mass of carbon is 12, and we talked about that earlier. I would like to add another point that molar mass and atomic mass, as mentioned right over there, is the same thing. It's just different ways of saying it. And if you're unsure where the molar mass is, always look at the key that is provided. For example, over here we have the atomic number on top and we have the atomic mass on the bottom, so we know which one we're looking for. So that would be the first formula that you need to know for for the chapter itself, stoichiometry. Alright, so we know the numbers, right? So first of all, we convert the mass of each element to moles. Grams. So what you gotta do over here is you have to get the number of moles. That's the thing over here, get the number of moles. How do you get the number of moles? Remember the formula? So to find the molar mass, we divide everything with what? We divide everything with MR, their molar mass. Each one has its own molar mass. N for N is nitrogen, that will be 14. Sorry, carbon is 12, oxygen is 16. Yeah, 0.04. Okay, divide by the smallest number to get a ratio. Now see, we have the number of moles. To this point, right over here, we have number of moles. The number of moles, that's right. Change the color from now. Alright, we have the number of moles till this point. Now we need to find a ratio. So we divide by the smallest number. The smallest number over here is 0.04. That will be 4. Even if it's 4.02, you could just write it as a 4. That would be a 1. That would be a 1. For nitrogen is 2. So let's just write the whole thing. N2. Let's just write the whole thing. N2. Because you can see over here, we did the working out for hydrogen and then we got 4. For carbon, it's 1 C. And for oxygen, it's 1 O. Where P is the pressure. P would be the pressure in PA cubed. And decimeter cubed, this is the conversion from decimeter to centimeter. It's better just to mention it over here. So if you have centimeters and you want to go to decimeters, you divide by 1000. And if you have decimeter cubed to centimeter, and if you want to go from decimeter cubed to centimeter cubed, then you want to multiply by 1000. But whenever you're using these equations, make sure that you have pressure in PA and you have the volume in decimeter cubed. Otherwise, these formulas might not really work and you would get the wrong answer. N is for the number of moles. N is the number of moles. And the number of moles that we found right over here is the exact same thing. Alright, just keep that in mind. Number of moles. R is the gas rate constant. So the gas rate constant would be 8.31. PV equals nRT. We have pressure, and we know that solids don't have pressure. And if we ever have pressure, that would always be a gas. So this equation can be used, should be used for a gas. And temperature, T for temperature, which is in Kelvin. Degrees Celsius, you need to remember how to convert back and forth from Celsius to Kelvin. If you want to go from Kelvin to Celsius, you add 273, then you need a negative 273. You need to subtract from that to get Kelvin. You could always substitute things, right? You can substitute N for this N over here. So if you have a question relating gas and it's asking you for the number of moles, you can find it using PV equals nRT. But if you don't have, for example, if they ask you for the mass, all right, they ask you for the mass of a gas, and they give you the pressure, they give you the volume, and they give you the temperature. You will find, you have all the information to find N, which is the number of moles. And when you have N, you can use this formula over here and find the mass using algebra and just solving it just for mass. You can definitely do that. C is the concentration and V is the volume. The concentration is in decimeter cubed. Alright? C is the concentration and V is the volume. You can see that we can, using algebra, we can subtract that because it divides out, and we have mole, which is the same thing as the number of moles. And we could use that for to find the number of moles or the concentration or the volume of an aqueous solution. 0.4. This is for a gas. This one is for a gas, and this is at STP, and that is standard temperature and pressure. What you need to know is, so sometimes the IB, I found this really confusing, but they would ask you a question and they would say at 298 Kelvin. So if it says 298 Kelvin, it means at standard temperature and pressure. And you can use this formula number 4. You can use that over there. Also keep in mind that they might ask you a before and after question. So for example, I give you a question that says if I have a gas at a certain pressure and a volume, and I increase the pressure to be 2 times more than the pressure was before, what would be the temperature? What would be the new temperature? I ask you that. So I gave you the previous pressure, I gave you the previous volume, and I gave you the previous temperature. I gave you all of these. And I give you the new pressure, and I give you the new volume. But I ask you, what would the temperature be? You can solve that using only this equation. Even though you don't have number of moles, you can do the following. PV over RT. Just bring that down there. And you have equals to N. You know that the number of moles before and after did not change. They did not change. So P1 and V1 and T1, they would be equal to the after the change of P and V, P2 V2 over R T2. The number of moles before and after remains the same because you did not add anything. You only increase the pressure. So then you can substitute this formula for this one. You could substitute N for this N over here. You could substitute all the information in. Straight away you could cancel the R, which is 8.31. And yeah, just solve for what they ask you. The same method could also be applied for number 3, where they change the concentration and they ask you for the new volume, for example. And you can make N equal to N. So that's just a side note, really important. I want you guys to understand that. Substituting the different formulas to find the before and after. And I think that's everything you need to know. Make sure you go through the problems. I think you have all the basics now. The only thing that I would do after this is I would definitely go through the different questions. Maybe go through the different IB problems that you might get, because the IB problems can be tricky at times. So yeah, I hope you benefited from this short review. Hopefully it wasn't too long. How long was it? Hopefully it's not too long. But yeah, if these videos help other people, I'll definitely be willing to make more videos like these. Thanks for watching.